So first of all, it's a pleasure for me to be here for a number of reasons. And I think one of the main ones is that I'm not visiting Hungary. It's a place that has become a new home for me. I come here several times a year. I have been doing that now for a few years now, and I have a few more years, at least in this project, to continue doing the same. So it's very nice to be integrated more and more into this community and into this country. And what I want to do today is tell you a little bit about the research that we have been doing over a period of about 20 years. So this is in some way a very condensed version of an effort that started, in the middle of the 2000s, and that tries to understand how countries develop, but using tools that are not the ones that are used traditionally in economic theory. These are the tools of economic complexity, which are related to machine learning. But to motivate that, what I'm going to do is I'm going to start with a story, and this is the story of a designer, which is called Thomas Thwaites. So let's see if we can, there we go. Okay, so I don't know if you know the story of Tom Thwaites. Tom Thwaites was a British designer that in the year 2008 was doing a master thesis at the Royal College of Art. And like many master thesis students, he had to produce, like some final project. So he decided, that he was going to build a toaster. Okay, and you can think, well, for a design student, for an industrial design student, a toaster doesn't seem like a big challenge. It's a product that you can find almost in every place, But Tom, of course, had a very clever idea in mind, because he didn't just want to build a toaster, he wanted to build a toaster from scratch. What did he mean by that? He meant that, well, he was going to go into the mines and trying to collect the iron ore that he needed to smelt to produce the metal parts of the toaster. And he was going to ask people in Norway if they could take him out in an offshore oil rig to be able to get the oil that he would need to produce the plastic. Now, that part failed. He eventually ended up using recycled plastic, but he tried as much as he could to produce this toaster from scratch using relatively simple, materials and procedures. And eventually, he did succeed. He did produce a toaster. But the toaster that he produced, of course, is not up to the standards that we're used to. And the point was that, of course, he didn't just want to build a toaster. He wanted to illustrate a point. It was more of an art than a design project in that sense. And the point that he wanted to illustrate is this idea that the world works not because there's a few people that know a lot, but because there's a lot of people that know a few things. And what the economists do is put that knowledge together. So basically what we're going to be doing today is looking at representations of the economy that honor this idea that knowledge is highly distributed and is very specific. And we tend to ignore that fact because the economies work so well, that the knowledge is put together constantly without us noticing that there is a lot of magic underneath that process. So economic complexity is the study of these development outcomes using, machine learning methods applied to economic data. And you might ask yourself, why do we want to use machine learning methods? Why cannot we use, traditional tools like the ones from calculus or statistics, which of course, we also use in parts of the process? And the reason is that machine learning is very good at dealing with a particular aspect of knowledge, which is hard, to mathematize, which is the idea that knowledge is non-fungible. So knowledge, is an important factor of production, is the secret to economic growth, but in reality, it's not a thing. It's not something like water that you put into a cup and you put more knowledge and knowledge comes up. It's not something that is undifferentiated and can be easily aggregated. It's something that is very specific and is not interchangeable. So you cannot take, for example, a surgeon and change that person with a pianist, even though both have high levels of education and high levels of manual dexterity, because the knowledge that they have is very specific to the activities of playing piano in a concert or performing surgery. So that non-fungibility means that if you want to really understand knowledge, you have to have a method that allows you to keep track of the identity of the elements involved and their interactions throughout the analysis. The moment that you aggregate, which you can do, for example, in measures like GDP, we aggregate across a lot of different activities, you lose information about that identity. And if that information is valuable, if that information about structure matters, you're going to lose the ability to understand how that structure impacts those macroeconomic outcomes. So machine learning is good at this, and we know that it is good at capturing the identity of elements involved because we have been able to use machine learning to do things such as generate language. So you've all used probably tools like ChatGPT or DeepSeek or Grok, that generate language. And the reason why these tools work is because they have representations that are unique to each one of the words that they're using, in this process, okay? And this representation is not the one that we learn at school. At school, we learn to represent words in terms of verbs, noun, adjectives, adverbs, and so forth. We have this part of speech representation of words. But this part of speech representation of words is an aggregate representation in which, we basically are grouping words that perform a similar function, not that have a similar meaning. Yeah? So, a chair is a noun, but like people are nouns too, are proper nouns, their names, and of course they're not clearly interchangeable. So if you change, for example, the word dog for the word chair in a sentence, the sentence, might lose meaning. It might mean something completely different, and these aggregate representations, even though they're not wrong, they're not able to capture the identity of each one of these elements of these words, because in reality, they are categories that are grouping things together. The same happens in physics when you think about, for example, the states of matter. There are many things that can be a liquid, Water is a liquid, alcohol is a liquid, you can have maybe acetone as a liquid, but if you drink each one of them, you're gonna have very different effects. The fact that they're liquids, is, it's a macroscopic, state, not something that, represents the meaning or the composition of each one of these things. So what we did in computer science was that we renounced, this representation, and we developed other representations that are able to trace the identity of each one of these elements, which is this idea of word embeddings. So every word now is represented by a unique vector, in a larger, vector space, and these representations are able to capture something that is closer to meaning. Now, how do we know the meaning of words? Well, because we know which words appear together in sentences or which words are used in which context by mining large number of text. So in economics, we have a bit of a similar problem. We have representations that are similar to this part of speech representation of, words. We can talk about manufacturers or agriculture, but manufacturing an engine or manufacturing a shirt is very different. We can talk about labor-intensive or capital-intensive products, but at the same time, yes, growing wheat is capital-intensive, manufacturing an engine is capital-intensive. Again, they're very different type of activities. So we need a representation that is able to capture the identity of each one of these elements involved, of each one of these economic activities. So the analogy here is that just like we can count the number of words in each sentence or in a paragraph to understand their meaning, we can count the number of activities present in each economy as a way to try to understand or to create a representation for those activities. So think that every country is like a book, okay? And the activities that a country performs are the words that are being used, to write, the narrative of that country's economy. And we're gonna use information about which countries produce which products or which cities, participate in which industries or which universities participate in which areas of research as a way to kind of like create representations of each one of these activities and each one of these economies in a similar way in which we're doing representations for words. Now, does anybody care about this idea of economic complexity? Is this just an academic exercise in which we're trying to create a better representation of economies because academics, of course, they're always interested in improving the methodology that we use to describe the world through math? And the answer is no. Actually, a lot of people do care about this that are not necessarily doing it for academic purposes. So economic complexity became recently the #1 mission of Malaysia's new industrial master plan. So Malaysia, a couple of years ago, released a new industrial master plan. This is like a Vision 2030 type of document in which they proposed 4 missions for the Malaysian economy. And the first mission that they proposed was advancing, economic complexity. Here in Europe, there was a famous report by Mario Draghi last September, and in that report, one of the things that they looked at was at the position of the EU compared to other economies in key technologies related to renewables or artificial intelligence, energy production, and so forth. And what did they use to see whether Europe was in the frontier or not? Well, they used the concepts of relatedness and complexity, which I'm going to learn about later. A few weeks ago, I was in Spain together with the Minister of Industry and Tourism, and together with the Cotec Foundation, we launched an observatory of Spanish exports and imports, a trade observatory, because also, this is something that is being used now in some places here in Europe. So we have done this in many parts of the world. We have built dozens of economic data observatories that are helping people understand where economies are and where they are going. So people outside academia care about this idea of economic complexity, and they care about using it. So what we're going to do today is we're going to learn about two key concepts that are the ones that are the foundation for this literature. The first one is the idea of relatedness, and the second one is the development of complexity indexes. So let's start with relatedness. This has very little battery left, I think. Let me get closer. So the first thing that we need to understand the concept of relatedness is this idea of proximity. And proximity is a way to define like some sort of geography of the activities that might be present in a location based on how cognitively similar they are. So here you see, like some sort of geography, but it's not a geography of mountains and oceans. It's a geography in which, the places are products, which are represented here by nodes, and the paths that connect them, the roads, are these links. So for example, in this geography of, products, you would see that printed circuit boards, are a product that is proximate to audio and video recording accessories. And audio and video recording accessories is a product that is proximate to electrical capacitors. But for example, here you don't see sunflower seeds because those would be products that would be in a very different part of this space. Yeah? So you have kind of like a network of cognitive proximity. And that defines like a larger space in which you have like clusters of activities that are related, and also you have many activities that are maybe not related to many others that hang out in this periphery as like these little twigs or branches out of this space. And you can now use that network to try to understand how far an economy is from an activity. Okay, so how far is Budapest from the aircraft industry? Or how far is Paris from the pharmaceutical industry, and so forth? And what you would do is you would overlay, the pattern of an economy over this network, and you would see which are the nodes that are close by. So in this example here, we're looking at the economy of Chile in the year 1979, and you see that most of the nodes are turned off. It's mostly gray, but here on the top right, you see that there's some bright nodes. Those are the products that Chile was specialized in 1979. So what this map is telling you is that, look, from all of the things that, the world can do, Chile is able to do well, well enough to be specialized in a few activities. And that also tells you that Chile is close to some other activities, because here we're not just telling you what these activities are, but we're putting them in some sort of a space that allows you to see what is close to them. So then when we run the movie forward, we can create this relatedness indicator, which is basically, a collaborative filtering type of metric, that would tell you what is the potential that an economy would have for each one of these activities. And the higher the potential, the more likely is the activity to, become productive in the future. So you see, for example, in 1979, there's a lot of nodes there that were gray that eventually become yellow by 1996, because diversification is a process that is constrained by this network of cognitive relatedness. So countries don't simply enter other products, they're way more likely to enter similar or related products. Okay, so let me tell you an idea, a story that illustrates this in a way that is maybe a little bit more cinematographic. And you all are familiar with Vespas, yeah? So very iconic motorcycle. It was also in the movie, what movie was it? In the movie Luca, exactly. But what you might not know is the story of who created Vespa. And Vespa was created by an Italian engineer by the name of Corradino de Ascanio. And what Corradino did before doing the Vespa is that he was actually, let me go backwards and forwards. Yeah, he was an aircraft engineer that was actually working mostly in the design of helicopters. So during the 1920s and 1930s, Corradino was a very talented engineer that designed many helicopters, some helicopters that even beat world records. And then during the Second World War, he was involved in the Italian army, and he was actually producing aircrafts for the Italian military. But when the war was over, a couple of things happened. One of them is that, of course, all of the Italian aircraft manufacturers had been bombed, so the factories were gone, and there was another thing is that, Italy was no longer allowed to manufacture aircraft after the war. Yeah? So they had a ban, a prohibition on the manufacture of aircrafts. So people like Corradino Ascanio needed to find another thing to do. No? What they didn't bomb, though, was their knowledge. Corradino had this knowledge on how to produce aircraft. He was a very good engineer, had a lot of experience in metalworks and so forth, and he had worked in the past with the Piaggio family, which was also a family that was involved in the production of aircrafts during the Second World War. So eventually Corradino, together with the Piaggios, they decided to manufacture a light vehicle that could operate in the streets that were full of holes at the time, in the aftermath of the war, which was the Vespa. It was a motorcycle in which this mudguard was also the body of the motorcycle, and that type of metalwork was metalwork like the one that they would use to shape metal in the aircraft industry. The front wheel, you can take it on and off, similar how you can take the wheel of a plane on and off. They use the same kind of like type of design. So this shows you that in this context of the product space, when you have a lot of people, let's say, work in a certain industry, and this industry literally gets bombed and people have to run away, they don't go away anywhere. They go, to a nearby industry, because this happened in Italy, but where it also happened, very similar stories happened repeatedly, was in Japan. In Japan also, a lot of companies that were involved in aircraft manufacturing after the Second World War, after their factories had been bombed and the prohibition on manufacturing airplanes was enacted, they started to manufacture light vehicles like small motorcycles, scooters, little cars, and so forth. So that's the idea of relatedness. Now, relatedness is not something, though, that is just about countries and products in the context of trade. What happened over the last decade is that many people started to study this idea, and we started to reproduce, this finding in a lot of different settings. So people would grab any data that they could find about the economic activities that are present in a location, and they would reproduce, this finding that the more related activities you had, the more related you were to an activity, the more likely you were to enter. So this became a principle because it was generalized across multiple geographies, multiple geographic scales. It's true for countries, it's true for regions, it's true for cities, and for multiple activities. It's true for products, it's true for industries, it's true for research areas, it's true for patents, And then we got together with a number of colleagues, now almost about, maybe 7 years ago, and we call this the principle of relatedness, which is a law. It's like a statistical law that tells you that the probability that an economy enters or exits an activity increases with the number of related activities present in that location. Great. So now let's look at Hungary in the context of, relatedness. So the Hungarian economy, as you know, is an economy that is very much focused on the production of cars, electric batteries. It's a very, let's say, mechanical engineering and automotive sector intensive economy. This is data that we present in the Observatory of Economic Complexity, and you can see that, for instance, with Slovakia, there's a lot of motor vehicle parts trade. With the UK, a lot of cars. In the case of Italy, also a lot of cars, but also, Hungary exports some wheat and corn to Italy and so forth. But when we look at this representation, we don't know what's close to the Hungarian economy or what is far from the Hungarian economy. So then we take this other representation, which is this product space representation, and you see that it's very different than the case of Chile. Hungary is very much here in the center of the product space, where you have, electric motors, cars, and so forth, but also there's some activity there in the electronic sector where you have, electric batteries, video displays, and so forth. You can go now from this representation, which is categorical and discrete, here you're seeing what Hungary is specialized in and not, to a representation in which every node gets a value, and that value is given by this measure of potential, which is this measure of relatedness. And then you will see that, for example, Hungary has high relatedness in all this central part of the product space, some relatedness here in the electronic cluster, but for instance, very little relatedness up there in the chemical cluster or in the garment cluster. Yeah? Now, the thing is that relatedness is a nice concept, but if you want to really measure potential, you have to go beyond relatedness, and create larger models of economic potential that include relatedness as well as many other variables. So one example of this is these bilateral relatedness models, which we have found to be very useful, to model changes in export patterns, and that we're using even right now as a way to power a simulator of the impact of tariffs in economies. And the way that this would work is that, imagine now, instead of having relatedness as a measure of how close is a country to a certain product, imagine that you have a measure now of how close is a country to export a certain product to a certain destination. Because maybe Hungary is really good at exporting cars, let's say, to the UK, but maybe Hungary is not so good at exporting cars to India. So for each market, now you can have a measure of relatedness. And when you do that, when you expand this, you can at least do 3 different relatedness metrics. You can do actually more, but you can say, okay, let's say Hungary exports, CPUs to Chile. Does that increase the probability that they would export a similar product like memory? Okay, or Hungary exports, CPUs to Chile, maybe because Slovakia and Austria, like the geographic neighbors, were already doing that. So that would be a story of like knowledge diffusion among geographic neighbors. Or maybe the knowledge diffusion is among the importers or among the exporter about similar importers. So maybe by exporting a product to Argentina and Peru, Hungary learns how to export it to Chile because they learn how to deal with the South American, importers or the culture or, how to do business in the region. And these are just 3 terms that go into a larger model that include a large number of different factors, like the previous exports on each one of these countries, the imports, their distance, their cultural similarity, and so forth, that you can use to measure potential. And what you do now is not just, a measure of potential of a country and a product, but for a country and a product and a destination that you can use to now create measures of future exports or future trade between those economies. So here we're seeing the highest potential exports for Hungary. You can do it by product, you can do it by country. So for instance, you see that when it comes to, exporting to Romania, maybe there is a potential to export a few more cars, vehicle parts, for the United States as well. But if you go, for instance, to another country like Brazil, you're going to see that the export potential is different because in the case of Brazil, you're going to see a product that doesn't show up in these other examples, which are pesticides, okay? So then you would start finding potential that is also specific to each one of these destinations. And that's how you eventually can bring relatedness more into practice by really having out these tools. In the latest versions of these tools, we get like a forecasting accuracy of about an R-square of 85%, in the models. So they're relatively good models at explaining, future trade. The next thing that I wanted to introduce is the idea of economic complexity. And this solves a different problem. Before we were trying to see the potential of an economy in an activity. Now, what we're going to try to do is we're going to try to score, the portfolio of activities that are present in an economy. Okay? So is this a portfolio of activities that is sophisticated and is conducive of future economic growth or lower emissions or not? How can we score the activities that are present in an economy? And the problem is that we want to score this in such a way that we don't make a priori assumptions of what activities are valuable. Because if we do that, if we assume a priori what activities are valuable, then we assume our answer. So what we will do is we say, look, we're going to say the complexity of an economy, K sub C, is going to be a function of which activities are present in that economy and the complexity of those activities. So the first equation, what it's saying is look, Hungary is a complex economy if it does complex things, okay? Okay, but what are complex things? I don't know. That's what the second equation is for. The second equation tells you complex activities are the ones that are present or being done in complex economies. So you say, okay, is pharmaceutical a complex economic activity? I don't know. Who does it? Give me the list of them, and then it's going to be proportional to the complexity of those places. Now, if I put the second equation in the first one, I'm able to get a self-consistent equation that I can try to solve for this K sub C, okay? And that tells me that this measure of complexity of an economy is going to be an eigenvector of this matrix of similarity between economies, okay? So I have a way now to estimate the complexity of an economy where I never made an assumption about which economies are sophisticated or which activities are sophisticated. It's all, coming directly, from the formalism. And it's interesting because this is a way to basically transform information on the geography of economic activities into a measure of the sophistication of economies and the sophistication of activities. Great. So let's look at this from a more intuitive perspective. So here we have a chart in which you have economic complexity index based on trade data. Then we're going to look at other examples that not use trade data. And here you have the GDP per capita of countries at PPP and constant $2011. And you see that there's a good correlation. you know. But what is interesting is not the correlation, is actually the countries that deviate from this correlation. So let me look at 4 examples here. So when we look at these 4 examples, you can see, for instance, on the top there you have Singapore, and Singapore is high on both axes, yes? So Singapore has very high economic complexities on the top, 10 of the world, and has a very high GDP per capita. And that would be an example of an economy that is rich and complex, okay? So it's an economy that is rich and sophisticated, so it sort of deserves that income in some way because it's producing things that are compatible with being rich. But then you have India and Philippines down there, and India, for instance, would be an example of an economy that it's poor, but is relatively complex. So that would be an economy that, according to us, and then we would see, in the models as well, is, destined to grow, okay? Because what this is telling you is that, look, even though the correlation looks very strong, remember that these are log scales on the y-axis, okay? So these are huge differences. So what this is telling you is that, look, India is relatively poor, but it has what it takes to compete like country with Portugal or Turkey, in terms of its capacities, But Portugal and Turkey are much richer than India. So India should be catching up towards those incomes. Then you have another country like Qatar, which is very rich, but it doesn't have what it takes, to be able to sustain, that level of wealth on the long term. Basically, it has like a few non-sophisticated products that produce, a lot of revenue, but not necessarily, support that wealth. And Liberia would be a country that would be poor and not complex. So it would be, quote unquote, in equilibrium, but it would be on equilibrium on the other side than Singapore, where, the economy is not sophisticated and the incomes are very low. Okay. So economic complexity is interesting because it helps us explain macroeconomic outcomes. So in 2009, when we first, introduced this idea, we found that it was good at explaining future economic growth. And that's a finding that has been replicated a number of times, by different people and variety of settings as well. Subnational settings in which people look at regions or states, many different examples also in an international context. But then we have found that economic complexity also impacts other outcomes. It helps explain international variations in inequality. It helps also explain international variation in emissions and so forth. And there is almost like a cottage industry of finding new things that complexity seems to explain. There is a paper, I think like a year ago, I remember seeing a paper in which they show that complexity, after controlling for a number of things, explains, differences in obesity, for instance, among other things. So it's a very robust, variable when it comes to predicting, macroeconomic outcomes. And one example that I like to illustrate of that predictive power is the work of the economic historian Giacomo Domini, which gets very close to what we would think of as an instrumental variable. So what Giacomo did is he collected data from the 19th century from the World Expos that were being conducted in Paris. So, France used to conduct this famous World Expos in which countries from across the world, would bring their products and they would show them to others. And what Giacomo said is, well, if a country is bringing a product to the World Expo, it's because they're trying to show the things that they want to sell. So these are their exports, So if Uruguay is showing leather shoes, it's because Uruguay can export leather shoes. And he collected that data, he digitized it, and he used it to construct, export matrices for countries in the 19th century. And then he used that data to calculate an economic complexity index of countries in the 19th century. And then, using that data, he shows that you can predict growth in the 20th century. And what to me is very interesting about this is that you have a regression that has only 96 observations, has country fixed effects, meaning that you're controlling for the fixed characteristics of each country, with 33 countries. So you have very few degrees of freedom in this model, and still you have a very strong and significant, prediction of growth in the 20th century coming from economic complexity in the 19th century. And this gets close to this idea of instrumental variable because nothing that happened in the 20th century can affect that variable because that variable was measured in the 19th century. Okay, so the 20th century had wars, had technological revolutions and so forth, but in some sense, part of the dice had been rolled and was already captured by the productive structure of countries in the 19th century. So as I told you, economic complexity also helps explain a significant amount of variation in income inequality. It's a relatively strong predictor of income inequality across countries and greenhouse gas emissions. In the second case, this is related to what we know as like the environmental Kuznets curve, and it's this idea that the emissions of a country per unit of GDP per capita, the intensity of emissions goes up and then down as the economy becomes more sophisticated. Okay, so when countries are like, say, low complexity and very poor, they have few emissions per unit of GDP per capita, per unit of GDP, then it goes up. But then as they become more sophisticated, they engage in activities that produce a lot of GDP per unit of emission. Okay, so they're much more efficient. Okay, now, again, this is not a story about trade. So here you have economic complexity for metropolitan and statistical areas in the United States. What is really interesting about this variable is that when you do work on the geography of anything, it's very likely that you get a map of population density. Okay? This variable is by definition orthogonal, to measures of diversity and relatively uncorrelated with measures of population. So let's look at complexity here based on patents, And when you look at complexity based on patents, what you see is that big cities like Chicago don't do very well. Chicago is a huge city, but technologically it's not very sophisticated. In Texas, the one that does best is Austin. It's not Houston, it's not Dallas, Miami, also huge city, doesn't do very well. But Boise, Idaho does very well because that's where Micron is located, and it's the only place in the United States that is able to manufacture computer memory. Rochester does very well in Minneapolis because that's, where the Mayo Clinic is located, and that's a huge, medical center, for medical innovation. So you get something that highlights relatively small places in the US compared to the big ones because you're capturing something about their ability to do sophisticated things, not just about their size. And this, of course, is not just about, the world and the United States, but it is also something that has been applied to other geographies. Here you have economic complexity, in China, you get, Beijing, you get Shanghai, and you get down here Guangzhou, Shenzhen, which are sophisticated areas as well. And here you have another example from Mexico, calculated by us in Data Mexico or by the Central Bank of Mexico. Mexico is a very interesting case, because it has a very polarized economy. The north of Mexico is way more sophisticated than the south. So if you go to like states like Nuevo León in the north, where the city of Monterrey is located, they produce cars, they produce electric batteries. It's very similar in some cases to like what you would think like as the Hungarian economy. It's a very automotive intensive economy. When you go down here to the south in Guerrero, the exports are going to be like guava fruits and maybe some coffee. It's a very different type of economy. And you capture that, economic polarization, but also, what you get to see is that economic complexity also predicts future economic growth at this level, and you get this 0.4, the same that Giacomo Domini got before. Very different context, and you get a very similar, estimate. It's about like one standard deviation on economic complexity gives you like about a 4%, annualized growth, which is huge. Now, economic complexity has been great, and I think a lot of people have adopted it because it has this robust ability to predict economic growth. And in general, it's a measure that it's a little bit ahead of our perception, okay? Like it tells us that some countries are gonna grow before the public opinion kind of like agrees on it, So it would have told us, for instance, in the 1970s that Korea was doomed to grow, when people didn't consider it. It tells us now that Vietnam and India and Philippines and Indonesia are rockets of growth, that are going to continue to grow over, the next decades. But maybe Indonesia and Philippines are not in your map of highest growth economies right now. But it also has some limitations. So when you calculate economic complexity using trade data, you are going to have a bias that is going to favor economies that are integrated to the value chain of their neighbors. Because you're working with physical products, and the highest complexity physical products are not the ones that are at the beginning of the value chain or at the end of the value chain, but in the middle of the value chain. Remember that we're using very disaggregated data. So it's not that you get kind of like a product like cars, and a country that exports cars gets the full credit for producing the entire car. Cars in this classification are made of about 400 to 500 products. Okay, because you have separate categories for tires, for engines depending on how many cc's they have, for different engine parts, for the shock absorbers, for everything, the transmissions, they're all separate. So for example, a transmission is a more sophisticated product than a finished car, okay? In terms of the geography of where it happens. It happens in few sophisticated places, while cars are assembled in more places. And that means that countries like Mexico, Slovakia, Czech Republic, Hungary, they basically tend to be overvalued when you look at complexity using trade data. And countries like Australia, Chile, or New Zealand tend to be undervalued, because if you're manufacturing a certain component for a car and you're in Germany or the United States, you don't want to manufacture that thing in Australia. Yeah, that round trip, that conversation on the phone, it's all a pain. You want to manufacture it in the north of Mexico, you want to manufacture it, in Slovakia. So for a long time, people were trying to fix this problem by trying to, do some changes or modifications on the math, but in some sense, you cannot get apple juice by squeezing an orange, no matter how hard you try, like at the end, this is something that was already in the data. So what we decided to do a few years ago, and it was a simple, but ended up being a very powerful idea, is to say, you know what, the formula is fine, let's just apply it to different data sets, because maybe these different data sets are going to have complementary biases, okay? So it's not that the biases are wrong, in some sense, the biases tell us something that is informative, but maybe if we take data from trade, from patents, and from research papers, we get complementary biases. So that is what we did, and we started estimating measures of economic complexity based on other, quantities simultaneously. So here you have economic complexity based on patents. And now Australia is doing really well. Australia was doing very poorly before. And Mexico is not doing so hot, and Slovakia is not doing so hot either. And this is telling you, well, maybe Slovakia and Mexico are manufacturing these sophisticated products, but they're borrowing the knowledge because they're not really innovating in them. Right? While Australia might be exporting products that are not very sophisticated, but maybe they're very sophisticated in the processes that they use to produce those products, and that is expressed, in their patents. And when you do research, you also, find an effect, as well, that it's complementary. So here, like the US does really well, Australia does well as well, and for instance, China is not so hot when you look at research compared to when you look at products, and the same happen, with Central Europe. So these measures are correlated. If you look at complexity based on trade and technology, they're correlated. They're capturing some of the same thing, but what is different is still important. So here you have, again, the example of Australia, very high in complexity in technology, about average in complexity when it comes to trade. Here you have research complexity, again, for example, the Czech Republic, very high on trade, low in terms, or lower relatively in terms of complexity based on research. And when you put these things together, you get better models of economic growth, inequality, and emissions. So these biases are complementary and useful. So when we run our forecast for the next 10 years, we see that, well, most growth in the world we expect is going to be in South Asia. Okay, so India is the highest growth economy in the world according to this, and Hungary is not doing bad. We predict an annualized growth rate of about 2% a year for the next 10 years, which is a little bit higher than what we would expect, for instance, for Western Europe. Yeah, but it's not like the 5% that we would get for India, over the next 10 years. Okay. Let me go like this. Yeah. Okay. So let's look at Hungary from this perspective. So in trade, as I mentioned, Hungary scores very high in terms of economic complexity. It's 14 in the world, according to the 2023 data that we have. But in technology and research, Hungary doesn't do poorly, but it doesn't do as well. So it does here, number 31 and number 30, meaning that the export structure tends to a little bit overvalue, the complexity of the Hungarian economy. There are other places where we could improve. Now, what we have been doing also is continuing this idea of multidimensional economic complexity by going beyond data sets that exist, but by trying to create data sets of our own. And one of the things that is an important trend that it's hard to collect using administrative data is information on trade on digital products. So when you open Netflix at home, you are technically engaging in international trade because you are importing, a product that was produced in the United States, and that you're watching here in Hungary, but that trade did not flow through a custom agent. Yeah. So it's not necessarily going to be counted, in international trade. And the way that it is counted also, might be a little bit misleading because it might be that there is a subsidiary here that collects those funds, but in reality, these funds, are then transferred, to the headquarter location. So what we did is we said, well, we need to capture that trade in digital products. So we started a project a few years ago in which we started collecting information on the revenues of companies, of large internet-based companies, and digital consumption patterns from the App Store and from Google Play. And we created a machine learning model that eventually was able to provide, bilateral digital product trade estimates for 189 countries and 31 sectors. So basically this would tell us how much did Hungary import from France in dating apps in this year, or in cloud computing services. So for each pair of countries and for these 31, detailed sectors, we would have that information. And when we look at the location of the headquarters of these companies, we also have subsidiary assignment location. We see that the world of digital trade is much more one-sided than the world of physical trade. And that makes sense because every country has to export some sort of physical product. Trade is not something that is optional. Sometimes some people tend to think that trade is optional. It's not, because no place can do everything that they need. Everybody has to, get some things from abroad, and to be able to pay for those, you have to sell some things, to those people that are abroad as well. But not everybody has to produce digital products. You can be a net importer of digital products that you're paying with your physical products. And in the case of the United States, we see that the United States is a very big net exporter of digital products. So part of the US trade balance deficit, is explained by the fact that California, exports through routers and imports through physical ports. So they're paying for all of those physical imports, all of that trade deficit, because Netflix, Airbnb, Meta, all of these are companies that are export companies. They're highly global operations, and every time someone buys an ad on Instagram here in Hungary, well, that's an export for Silicon Valley, that it's taking place. So it's a very one-sided, with the US first, China second, and the EU, third, but also with companies that are relatively old, like SAP, for instance, or Amadeus, in that space. Digital trade, however, is growing very fast, So in terms of annualized compound growth rate, it's growing about 25% a year, which is, that's a rocket for any macroeconomic statistic, It's extremely, fast. So that means that basically every like 3 years, you are doubling, the volume of digital trade. In the paper, we calculated all of this up to 2021, because the paper had to go through review. It's a long process, but now we have estimates going until the end of 2023 and hopefully until the end of 2024 soon. But what this slide tries to show, or argue at least, is that you cannot neglect this category, even though it's relatively small compared to physical trade. Trade in physical goods is like 22 trillion, but digital products are just about $1 trillion, maybe getting close to 2. They're maybe, 5 to 10% of physical product trade, but they're growing much faster, So it's a train that you don't want to leave behind. And when we include, these digital products in the exports matrix of the world, we find that actually digital products tend to be of high complexity. So they tend to occur in few countries that tend to be diverse and do sophisticated things. So adding digital products to trade data, helps us refine our measures of complexity as well, because these products tend to be sophisticated. So to conclude, I wanted to show you a couple of other examples that are not so forward-looking, but a little bit more backward-looking, because at the end of the day, there's two things. One thing is that what we have done so far is we have developed these machine learning tools that are helping us, create measures of economic potential or create forecasts about, the economy that capture information about economic structure that is useful and that escapes, aggregate statistics. But in reality, these exercises of imagination, these exercises of forecasting can be applied to the past as much as they can be applied to the future, because there's also a lot that we don't know about the past, and the past is also something that we need to reconstruct, in some way with incomplete information. So what I'm going to do is I'm going to show you two projects that use now historical data and some of these methods to try to answer, some scientific questions. The first one is related to the role of migrants in the flow of knowledge. So it is very well known that migrants are very important vectors of knowledge flow. So there's a lot of papers, and there's a lot of stories that actually tell you that the ability of a country to start producing a new product depends in many cases of a migrant that arrived with that knowledge on how to produce that product from a different location. In the book that I'm releasing later this year, there's a beautiful story about Samuel Slater and how Samuel Slater, as a 21-year-old, helped develop manufacturing in the United States, by bringing that knowledge secretly from England at the time of the revolution. I think here in Hungary, probably like a famous story is the one of the ball pen. The guy that then went to Argentina, Laszlo Biro, and did the ball pen. And, Argentinians claim that, as their invention, and I'm sure here it's claimed as a Hungarian invention. So there's a lot of stories that migrants are well-known vectors of knowledge flows, but, all of this research is done with relatively recent data, patent data, publication data. So it's all research that includes information from the 20th century. So what we wanted to do is to say, well, is this something that is a recent phenomena, or is this something that is a more historical phenomena? So what we did with Philip Koch was to study, this phenomenon by using information on the places of birth and places of death of, dozens of thousands of famous individuals. So we grab these biographical records, and we know, where a person, that is famous in many languages in the Wikipedia was born and where they died later. And we can use those flows as a way to estimate, how people were migrating or moving. Yeah, because you say, okay, if, let's say, Pablo Picasso was born in Andalusia, but then he died in France, that's a knowledge flow or some sort of movement from Spain, to France. And most people that are famous enough to be on Wikipedia in many language editions, they die in a different place that they were born, So, of course, that helps, because they were known in different places because they moved around. So we grab that information, and we use that to reconstruct these networks of knowledge flows. And you see that these migrant networks, they tend to concentrate a lot towards the capital places. So there is a lot of movement in France towards Paris, and there's a lot of movement in Italy towards Rome, and there's movement in Hungary, you see, towards Budapest, or in Russia towards Moscow. In Germany, there are like two centers, there's Berlin and Munich as the two main centers of attraction. And what is interesting is that, for example, if you look at this chart, the green line shows you how many different places people are being born, people that become really famous are being born, and in red you see in how many places they're dying. And you see that starting more or less like in the 15th century, there is a split, meaning that, talent is everywhere, but it develops only in a few places. People that become famous are born anywhere. There's an increasing number of places, but there are very few places in which they end up. And here you have the share of migrants. You see, it's about like 75, 80% of the data set. So most people, died in a different place that they were born. So we can use this to, again, create measures of relatedness, and I'm going to explain them here, in a relatively simple language, because we have migration now between both locations and activities. So you can move, let's say, from Nice to Paris, but also you can have spillovers that happen between activities. So the first thing that, we would look at is, for example, do migrant mathematicians increase the probability that local mathematicians would be born and become famous in the future? And that's an effect that is very well established in the literature. All of these stories that I told you, before, is someone that had knowledge on something, and then they go to another place, and the knowledge on that same thing starts growing in that place. But you can also ask yourself the question, well, are there knowledge spillover between locations and between activities, for instance? So that's, the arrival of many famous physicists increase the probability that there will be famous mathematicians or famous chemists in the future. And you can construct, measures of relatedness for each one of them. What we do here, to be very careful, is that we construct a measure of excess migration. So it's not if you receive a migrant, but if you receive more migrants than we would expect based on a null model, we're going to count that place as receiving enough migration, kind of like to have a shock or an effect. And using these measures of, excess migration, we create measures of relatedness for the immigrants, for the emigrants, and the locals. So what we're interested in is like, okay, if there are new activities appearing in this place in the future, who are we going to blame? Are we going to blame the immigrants? Are we going to blame the emigrants, the ones that, were born here but left, or the locals? Are we going to compare, these three effects? So now we can transform, that matrix into certain, estimators that we have for each one of these different variables. So, for example, the excess number of immigrants that you receive in a certain location with a certain specialization at a certain point in time, or the number of people that were born in that location, that would be the effect of the locals. And then you have this relatedness, which would be like the excess number of immigrants that came with knowledge that was similar, but not the same of the one of that activity, and so forth. And when you throw this, into the entry and exit models, what you find is a couple of things. The first row, is the direct effect. So if more mathematicians migrate to a place, that place is going to produce more famous mathematicians in the future. Okay, so there's an inflow of excess mathematicians. That's a strong effect, and you see it on the top, very significant, very consistent, and we control for a lot of fixed effects. We have like about 700 fixed effects here. So this is not because a university was open in that city at that time that attracted the migrants, because we're controlling, for instance, for fixed effects for the region and the time period, and that will be captured by that thing. Also, if you have more mathematicians that, let's say, migrate, you have a reduced probability of losing a specialization in that activity. So it helps you preserve, that activity as well, and those are the negative coefficients from column 6 to 10. But the relatedness terms for the immigrants also, tends to be significant. The ones there, you see it in model 2, 5, 7, and 10. It's not as strong as the direct effect, but it's significant, and the other terms are not significant. So what this is telling you is that a lot of like this diversification story, actually, is a story of knowledge flows, that are carried by migration. The locals, at least in these estimates, do not seem to go to the dance. The direct effect of the locals, like they tend to be, insignificant. So what this is showing is that the ability of a place to enter new, in this case, cultural activities, increases quite dramatically when you are attractive to people with that specialization, or when you're attractive to people that are related to that specialization. And this goes back several hundred years, so that's another thing. The final project that I wanted to show you is also a project that is focused on economic history, but in this case, what we try to do is to try to reconstruct the economic history of Europe and the United States, again, using information from biographies. So the problem that we're trying to solve here is that historical GDP per capita data is very, very sparse. Okay, there are very few, estimates. So if you go to the Madison Project, which is kind of like a gold standard in this field, you go back to year 1300, you have basically 5 data points. You have an estimate for Northern Italy, you have an estimate for Spain, for Sweden, but you don't have information of the GDP per capita or estimates of the GDP per capita for many other places in Europe. Even for the year 1750, you still have relatively few estimates. So what we wanted to do is to go from there to there. That's what we did, okay? So this is the gold standard from 1750 right now, and what we did in our paper is reconstructed, the GDP per capita of European regions now. You see, we're going from countries to regions, using these machine learning, models. And we have a lot of ways to validate this. So again, what we're using is information about biographies, about like 500,000 famous individuals assigned to about 50 occupations with places of death and birth across all of Europe. And the reason why we do this is because this is relatively fine-grained data going back in time quite a lot. So you see that for the 1300s, we have 6 data points for GDP per capita, but we have hundreds, maybe thousands of points about biographies for these different locations. So it's a very high resolution data set, for that. And the reason why we use biographies is because here we're not after a causal story, we're looking for a correlation, and biographies should be correlated with wealth, for, let's say, two reasons. There is a direct effect. So maybe if you gave birth to someone like James Watt, James Watt contributed to the growth of your economy by producing the steam engine. But maybe if your economy is able to attract famous painters, famous musicians, famous singers, it's because these people are looking for places that are prosperous enough to support their artistic activities. And therefore, the death of famous painters and famous musicians means that this is a place that was rich enough that people could develop themselves in these artistic endeavors. So they did not cost the wealth, maybe they were attracted to it, but we don't care because we're just looking for variables that would be correlated with the wealth of a place. Okay, so what we do is we set up, a regularized elastic net model, with a very already high baseline, and that model allows us to explain about 90% of an out of sample prediction. So what we do is we grab the data, we hide 20% of the data, that the model never sees, and we train the model in 80% of the data. And then we look at the predictions that that model makes over the 20% of the data that it never saw. And that prediction, here, this is an example, but here you see like several repetitions of that. So the model as a median, it gives us, an R-squared of about 0.9, which is very high out of sample, prediction. And then we validate this, by looking at how it helps us reproduce several historical facts and events. So one idea is that there was a reversal of fortune between the north and the south of Europe. So in the year 1300, the south of Europe was richer than the north. But then, the north of Europe became richer over time, and when we look at our estimates of GDP per capita, we're able kind of like to reproduce that fact with a crossing point here, basically on the late Reformation period. We also validate this by reproducing Acemoglu, Johnson, and Robinson Atlantic trade stories. So Acemoglu, Johnson, and Robinson paper from 2005 argues that countries that had access to an Atlantic port basically were kind of lucky when America was discovered, because now they had access to like an entire new continent that they could trade with, while if you were, for example, Greece, and you had ports all the way, in the Mediterranean, you would not have access to that Atlantic trade as much. So that exogenous shock of discovering America was more important to Portugal and England than to, let's say, Greece and, let's say, Bulgaria. Yeah? And we are able to reproduce that as well, that basically the GDP per capita of Atlantic port countries is the one that really shoots up, after, the discovery of the Americas. So on the left, you have the Acemoglu, Johnson, Robinson figure, and on the right, you have our reproduction in this paper. We also validate this with other proxies of economic development. So we look at urbanization rate, which is something that people sometimes use as proxies of economic development, in the literature, average height of people in the military, well-being index in 1850. And this last one is quite curious, is church building activity during the 1300s and 1400s, and the idea is that you can afford to build churches if you look at these churches that during the Renaissance or the late medieval period. These are churches that took hundreds of years to build, and you would have to put, let's say, your excess income or wealth into that production. These are days that the farmers are not spending on the fields. These are days that people are dedicated to build the church, and basically, the church building activity is higher in the places that we predict that they had, higher levels of income at that time. So now we can reproduce like the economic history of Europe. So here is our map of Europe for the 1300s. We have more than 5 or 6 points right now. And you see that in the 1300s, basically, it was all about Tuscany, and northern Italy were the richest parts of Europe. In the 1400s, Italy is still dominating. By the 1500s, we start getting a little bit, of action now in the Netherlands, and eventually by the 1600s, the Netherlands are doing really well in this type of estimates. By the 1700s, it's Italy and Netherlands again. And then you start kind of like getting now London, to show up in much darker spots, and eventually you end up in a world in which, the capitals like Paris and London are doing very well, but also we start getting estimates from the United States. And by the year 1900, for example, we estimate that many parts of the US were already richer than parts of Europe at that time. Parts in California, according to our estimates, would have been richer than many parts of Europe at the same point in time, which is a little bit controversial, but I think it's interesting because it shows kind of like a trajectory that definitely panned out later. So how do we put these ideas into practice? And here I'm going to give you like a few examples that might be interesting for people here in the statistical office. So the way that we have put economic complexity ideas into practice is by building these economic data observatories that I mentioned to you before. So this is Data Saudi. This is a platform that we have been building for many years now with the Ministry of Economic Planning of Saudi Arabia. It's a very active, project. Now we're moving towards, producing, for example, like, chat versions, that allow people to interact directly with the data, forecasting tools, the whole set of things. And this is something that we've done in many parts, as I mentioned before. This is another example, which is Data Mexico. This is the official data distribution platform of Mexico's Secretary of the Economy. And these are platforms that integrate a large number of data. Yeah, so they integrate data on trade, on industries, on safety, education, health, transportation, and so forth. In the case of Data Mexico, there's a very interesting story because we started building Data Mexico at the end of 2019. And as you remember, at the beginning of 2020, what happened? COVID came in and everybody had to become a worker in an eternal Zoom call. So what we did with Mexico was that the secretary decided to develop, a program in which they would train the statistical offices of Mexico around the world to use Data Mexico for their foreign direct investment efforts. And that was very successful. Like Mexico is an economy that basically works to attract foreign direct investment, to produce things that then they would sell into the United States based on the free trade agreement that they still have with them. And this was a way to basically empower all of those diplomatic units to help attract foreign direct investment. I think in the case of Hungary, there is a similar strategy that Hungary could be a gate to Europe for Asian partners, that could, and I think it already happens in some sectors like electric batteries and so forth, and this is something that really helps empower those diplomatic units by providing them with all of the data, with well-designed charts and all of that stuff. And of course, we have kind of like platforms of our own, like the Observatory of Economic Complexity for many years now is the #1 tool in the world to visualize international trade data. And this is also one of the ways in which our ideas make it into the world. So to conclude, economies are complex. And the reason why they're complex is because knowledge is non-fungible. Knowledge is not interchangeable. It's a lot of little pieces. It's an infinite alphabet of ideas and received wisdom that cannot be condensed into one thing. And to understand it, therefore, we need representations that are more granular, that allows us to capture each one of these activities separately and independently. So this is a shift in a paradigm. It's a change from the idea of size to the idea of a structure, So measures of size are important. Like I'm not, disrespecting measures like GDP. I do think they're very important and very useful, Just like knowing the size of a baby as it develops is very useful. But there's so much that you can learn just by knowing changes in size, because in reality, these complex systems that have a lot of components that are very unique, different, and they interact in a myriad of different ways, need to be understood through measures of a structure that allow to see each one of these components separately. And in terms of the way that we understand economies, this is kind of like a similar shift that we're moving from measures of size also to measures of a structure where we can understand specifically what is that economies do, because that structure is not irrelevant. Two countries that export the same in volume but export different things in terms of the quantities that they do of these different activities, they are qualitatively quite different. And economic complexity is that change in representation. It provides us these granular representations of economies that can help us understand where economy stands and where they're going. Thank you.